stuff. We have a couple extra weird fixed function things that, as time goes by, fixed function stuff keeps dropping off bit by bit, but we still have special hardware for rasterizing and stuff like that. But most of the time I'm going to try and talk about computing. Also, since this is a pretty large group with a lot of diverse experience, mostly from talking to Chris, I'm targeting the people who already know CUDA and compute a little bit. So I've got a ton of slides. I'm going to breeze through some of them really fast and slow down. What I'm hoping for is that if people have questions or want to drill into something, go ahead and pop your questions out. We'll drill in as deep to something as you want to drill into. If there's something pretty basic, I'll probably gloss over it. This is a bit of a Frankenstein talk because I've taken 20 different presentations and glued them together to try and get something that fits well. So we'll see. All right, so the first thing is basically just the motivation for GPUs and why GPUs. And we'll go through this pretty fast, but basically, things get a lot faster over time. And the expectation was that every 18 months, you're going to be doubling processor speed. And everybody knows it can't go on forever. When I was in grad school and taking architecture courses, let's call it 2003 to fudge a little bit, there was this neat chart that one of my professors showed that basically said, all right, here's the temperature graph of how things are going up over time. Now we're getting better and better at cooling things off, but somewhere right about 2010, 2012, our processors are going to be the temperature of the surface of the sun. So, something gives somewhere in there, and you can't always just keep scaling up clocks. I mean, it used to be that whenever you wanted to get a new computer, you'd say, what's the clock speed? How fast does this thing go? And I'm pretty sure none of you guys ever looked at that, at least seriously anymore. You're like, all right, it's fast, but how many cores does it have? What's the cache system look like? There's a lot of other things that you look at now aside from clock speed, because clock speed can no longer tell you that much. So yeah, you can kind of see where things are clustering around. So the basic problems, the reason we can't keep scaling up the way we have, the big one is power, right? As you get down to process size, Kepler is 28 nanometers. Intel, I saw some roadmap that they published, and they're looking at 5 nanometers in like 5 years or something ridiculous like that. Maybe not 5 years, maybe it was like 10 years out. But still, they're talking about 5 nanometers. So when you're talking about that, you've got a lot of power leakage out of the gates there. And the clocking to drive things just is a huge part of your power already. And you can't clock up, you can scale down and fit more on a die. But basically, at this point, we're not getting faster, we're getting wider. So on a CPU, you're putting more cores, you're fitting more into a given amount of space. But there's only so far you can take that. So yeah, you'll burn out your CPU, or you'll do really crazy things to get more speed, like 20% more speed. Memory, all right, so here's a really big thing, and I'll hammer on this later on in the talk, but memory is huge. Even if you have infinite processing resources to crunch on the numbers, if your memory can't keep up with your processor, if you're trying to do, it would basically be like if you had a jet engine and you were trying to feed it with a little sippy straw. At some point the memory can't feed the computation and you're out of luck. So you've got to find different ways to deal with the memory. And lastly, instruction level parallelism. If you've ever seen block diagrams for a CPU, if you look at the computation of the CPU, it's a very, very small part of the die. A huge part of the die, aside from, cache is like 2/3 of it now or something. But if you ignore memory and computation, everything else is basically logic on how to schedule things. Predicted branching, prefetching, out of order, reordering things, all sorts of, and really deep pipelines. And then you have to try and figure out how to chunk that up. And that just gets to be really difficult. There's been a lot of good work on that, but at some point you can only take IL2 so far. And so, like I said, I'm going to fly through some things because you probably already know that if you're here. All right, so CPU and GPU. I think at one time people would have liked to have said the GPUs are going to take over the world and CPUs will go away. I think the message is more that they're good at different things. You can ultimately think of the GPU as a highly parallel processor, and the CPU as a highly serial processor. The CPU is trying to get more parallel, and the GPU is trying to get more serial in certain ways. And Kepler, I'll show you kind of an example of what I mean by that. But they're designed to target different problems, and it kind of makes sense to have different architectures for parallel versus serial. Each one of those little cores in the GPU isn't nearly as smart as each core in the CPU, but we've got so many more of them. Ultimately, we have a lot more computing power, raw computing power in a GPU than we do anywhere in the CPU. And so this is just what I was talking about. The trick then is to figure out what problems map well to what processors. You know, if you're doing word processing, you're going to have a little bit of difficulty using the GPU well. But if you're doing computer vision and you're trying to, you know, do the next generation Google car that's going to be looking at all the other cars on the road and not hit that kid that's running out in front of it, you don't really want to do that on the CPU. You'd really like several GPUs that you can dedicate to that sort of problem. And so this is just kind of both throughput on memory and throughput on processing. You can see that GPUs are able right now to scale much better than CPUs and deal with really compute intensive things in a way that CPUs can't right now. All right, just a couple slides to kind of toss in something that I thought was kind of cool about doing compute stuff and why it's not just a matter of doing it a little bit faster. You can actually change really interesting things by doing things a lot faster. So processing CT scans, it used to be that, you know, the doctor would do something and, you know, you'd go in, you'd get your CT scan done, and then a couple days later they'd be done processing it, they could talk to you about results. Now, with some of the things that they've been doing with computation and parallel processing, you can actually get your scan within 2 minutes. And what that means is, if you get the results of your scan within 2 minutes, you can be right back in the machine and they can refine the scan. They can look at different things. They can change within that visit what they're looking for. And so that makes a big difference. The next one is actually kind of more mind-blowing, but it's well, yeah, basically by doing processing on real-time scans, you can actually stabilize an image and stabilize the tools that a surgeon would be using and essentially make a beating heart look still to a surgeon, so that a surgeon can operate on a beating heart because of real-time computation. So I mean, you can do things because of that increase in speed that you could have never thought about before. And one of the things that I find really interesting is, you know, I'm really down in the weeds about the architecture and the driver and the memory management and things like that. And so it's always kind of cool for me when I can see kind of success stories that we see coming in, weird ways in which people have used our stuff that it wouldn't have occurred to me to use it. So. All right, so that kind of gets beyond the motivation part of it. Now I want to talk a little bit about the architecture, if I can go on to the next slide. All right, so this is a block level diagram from the graphics perspective of GeForce 8. So kind of going back a little bit in time, but what's interesting here is that you can kind of see how the GPU structures things. We've got these processing cores, essentially. You know, each one of these little green dots is a separate processing core for doing something. And you can basically run, you know, a single thread on one of those green dots. Then, you know, we've got texture fetch units, we've got L1 cache, which is basically local memory to here. And so, you know, if you can keep everything you need to do in L1, you'll be pretty quick. L2 is not that far away, so if you need to drop down to L2, it's not so slow, but you're going to start seeing performance problems. And then we go out to the frame buffer, which is basically, you know, the GDDR5 or whatever it is that you've got on your board. That's what your frame buffer is. And so if you need to go all the way out to there, then suddenly, instead of looking at, you know, stalling for 18 cycles, you're looking at stalling at 800 cycles or something like that. So that's one of those trips that you want to avoid. So the reason I'm showing you this is, resolution-wise, it's a little bit easier to look at this slide. This was probably about 2007 or so. Now we get to GT200. This is 2008. I guess somewhere around 2008. So you can see it's not that much different. They just packed more in. Same basic architecture. All right, now we get up to Fermi. This was 2010. And so they packed more in and they've restructured things. You can see that L2 is shared in a different way. The communication between each of these things in L2 is a little better. DRAM IF that you see off on the side, that's still going off stock to the frame buffer, and it's a long way away, and you don't want to do it. And then this gets us to Kepler, which is what we just announced. So we've got a big L2 in there, and L2 is really what unifies each one of these. So they're called SM, which is streaming microarchitecture, I think. We come up with, so it's one of the problems with working for NVIDIA is that we're really acronym heavy. And so unfortunately I know all the acronyms, but sometimes when pressed I can't remember what they stand for. But basically what you can think of is one of these is, when you're programming CUDA, you've got your threads, you've got your blocks, and you've got your grids. But you can see on a block diagram like this exactly what that maps to. Each one of these little tiny green spots in there can run a thread. So for every green spot that we've got, that's one thread that the computer can actually be running, and all those are simultaneous. Now each one of these kind of clusters, each one of these SMs, that's a block. So each block will run on one of these, and you can run 15 blocks simultaneously. Well, I mean, perfectly simultaneously. It breaks down a little differently in reality, but that's basically it. And then the whole thing would basically be your grid. Yeah?
Why are there 15 and not 16?
Oh, well, that's a good question. I don't know exactly. However, one thing that we do is what's called floor sweeping. And so the manufacturing process, right, they stamp out a die for us. And it's 28 nanometer, and it's these silicon wafers, and I don't have something that shows it really well, but you can think of it as about like this size, this white bit's taken up. Now, when each transistor is on the scale of 28 nanometers down there, I can't even begin to show you how small that would be. Any little flaw you have in that silicon is huge. And you don't want to throw away the whole chip because there's a flaw. And you're going to have, on any given chip that you manufacture, a lot of flaws. So what you want to do is you want to find a way to mitigate that. And if you've got X number of flaws, you want to be able to isolate the units with flaws and chuck them out. So now let's say that we said that it was going to have 16 of these SMs. The chance that we would actually get 16 perfectly flawless one on every die, that's going to really lower our margins because we're going to have to throw a lot out. Now, saying 15, we feel pretty confident that we can salvage 15 out of 16, at least on our high-end parts. Now, by the time it trickles down to a low-end part, we might be only salvaging 8 out of 16. But having 8 of those for a part where you're paying, 1/10 or maybe 1/20th, or I don't know that end of the business, so I can't tell you, but I can tell you that floor sweeping is what dictates a lot of this sort of thing.
So you really have 16, but you have one for backup?
Well, we probably have 16 in the hardware, but they're completely masked off. So what we do is once it's manufactured, it comes off the line, and we run automated tests on these. Actually, TSMC in Taiwan runs automated tests on these and tells us what's good and what's bad, and then we can, after manufacture, mask certain things off. And it's not just whole things like this. It might be small blocks within it that we can mask off. I know memory is part of it. Memory is part of floor sweeping. There's a lot of things that come into floor sweeping. Sometimes you don't have to discard an entire part. Sometimes it's a matter of just clocking it down, and it works better. And so there's a huge amount. I wouldn't want to guess a percentage, but there's a huge amount of the business that goes into figuring out how to mitigate flaws and still be able to ship and make money and have a profitable business. Yeah.
Are these block diagrams like somewhat representative of the physical layout of the die, or is it just like strictly block diagram?
Oh, that's a good question that I don't know the answer to. Once upon a time, they were somewhat representative. I think now they're not as representative as they once used to be. I think this is a better attempt to be representative than, say, getting back to the GT200 stuff. This isn't very representative, but this is somewhat representative of how it's done, mostly because you can see that we've got this L2 cache running between everything, and then the L1 caches and kind of the control logic further out to the edges, which is actually how things would be done on the chip. But it's not exactly how it's done on the chip. So, all right, so that's kind of the highest level architectural view of how things are working on chip. I can go into more details on this if people want, otherwise I'll kind of start moving a little bit more into the software end. And I wanted to leave some time at the end for questions, and I also really wanted to go over some of the new things in Kepler, because I figure you guys know a little bit about how traditional GPUs work, you know a little bit about how CUDA works, but some of the new things in Kepler you may not be familiar with, and they're kind of cool. And I am biased, so. Oh, yeah, just to compare Fermi versus Kepler. So this is an SM on Fermi, and this is an SMX on Kepler. SM, SMX, just new names. But basically, over here you can see, you know, these are all the compute cores, these are load store units, these are special function units. Over here, special function units, general computing units, and load stores. So you can see that most of everything is just general computing. Special function units are doing things like cosine, you know, stuff that you wouldn't want to try and replicate in silicon. In general purpose stuff, you have special purpose stuff that is just for that, but it's done often enough that you've got a lot of it. Another thing that's worth talking about, and I'll talk about some more later, is this little stuff hanging down at the end, and this stuff up here. So it used to be that there was kind of this generalized L1 that just serviced everything, you know, all the needs of, all the local storage needs of these cores. Now it's broken out a lot more, so we've got a really large register file up here that's enough to give each thread 256 registers in Kepler, which, you know, when it used to be that you had 64 registers or, you know, 32 registers or something like that, then the compiler has a really hard time optimizing for what you want to do, and you start having what are called spills, which is basically you can't fit something in a register, so you've got to store it off to memory, load something from memory in, and then, you know, use it in the register and move forward. And you just have to swap things in and out of register. Now if you've got 256, suddenly the compiler has to, well, you've got more opportunities with what you can do for good performance. And I can drill into that if somebody's really interested, but down here we've got the L1 itself, which is split between shared memory and actual just cache. And if people are interested in how that works and what that's useful for, I can talk about that. Then finally, there's a read-only memory, which is new to Kepler. And it's basically, we can optimize in certain ways if you know that you're not going to write back. We can do certain kinds of prefetch. It used to be the only way to get that read-only memory was to go through the texture units and use a texture cache. And this is actually a lot better for compute. So again, one of the things that you'll see, I'm talking a lot about memory. In my opinion, half of all compute performance, whether it's graphics or compute, is how you use your memory. Memory is one of those things that you don't grow up thinking about in a computer. It's just something that's there. But if you want good performance, you really have to think about memory and how you're using it, what sort of locality you're getting, whether it's spatial locality or temporal locality. Memory is a huge iceberg under there, and it's the key to all of your performance pretty much. So lastly, and this is kind of starting to look at things from a software angle and not just a hardware angle, all of those cores have to get work scheduled for them somehow. And that's always a big problem. This is for Fermi, this is just kind of a software view of how things look. The CPU would send things down in these streams. You know, so we've got 3 different streams here, and the CPU sends it to the GPU. The GPU actually sees these streams and kind of picks things in a round robin. So it says, all right, I'm going to grab things from you and send you off to the work distributor. All right, if there's any more room, I'm going to grab things from you. I'm going to grab things from you, and it's going to send it down. And then the work distributor figures out, all right, what can we send to which of the SMs, and you know, how much can we have active at once? Now there's a catch though, and there's what's called the context. You can have like one app having one context, and it can have a bunch of different streams that are all running in parallel. But if you've got, you know, 2 different apps, 3 different apps, 10 different apps all running on a system, today, pre-Kepler, you would have had only one app ever running on the GPU at once. And so you would have had kind of non-optimal usage of your GPU. I'll show a slide that kind of compares Kepler later and how it does things, but that's actually changing where you can actually have multiple apps running at the same time, and the GPU is starting to manage itself a little bit more. So we talked a little bit about memory layout. This is an old slide that I just tossed in as an example. As much as you can keep local on here, on the GPU, you want to keep local. Same story on the CPU. I mean, it's the same whether you're talking GPU or CPU for memory stuff. As soon as you have to go into the caches, you start slowing down a little bit. But it's not so bad. I mean, it's designed, that's why the cache is there, is to keep it fast. Once you have to go out over a bus to main memory, main graphics memory, you get really slow. It's the same thing with the CPU. You know, if you're going out to your RAM to do things, if you've got too much to fit in the cache or the registers, it gets slow. Now, this is where things get really tricky when you're dealing with the GPU, is traditionally everything's launched from the CPU, you send it over here to do work, it has to go back there, and then you keep sending things back and forth. And the PCI bus, even though it's fast, traditionally, compared to other buses, it's tiny. That is a huge bottleneck that will drive a lot of your optimizations, avoiding going across that. You want to cross that bridge as little as you possibly can, because that's going to make your life hurt. And it's one of the biggest problems in video games, is if you want your game fast, you have to have as much resident on the GPU as you can, and you have to have as little communication back and forth across that bus as you can. So one of the problems that we face in designing GPUs is how to make it so that people can stay just on the GPU and not have to go back and forth so much.
How big is video DRAM usually compared to the system?
So I'd say I think the sort of graphics cards that we ship that might be in your laptop, you're looking at like 512 megabytes.
Okay, great.
You might have a gigabyte. If you've got a Tesla compute card, you might have 6. I think they're talking about some that might be as much as like 16 gigabytes now.
Same order of magnitude as
Same order of magnitude. It also tends to be that we're using kind of a beefier, a more expensive kind of RAM. So the GDDR, which is generally used in the top end, is a more expensive kind of RAM. And so it's part of the cost of the board you're paying isn't just the GPU, but RAM that's going to be more expensive than what you're used to using with the CPU. And the caches in question, I think Kepler now has, and you probably know this better than I do, but I think Kepler has a 2 megabyte L2 cache. The L1 caches are 64K, I think, per, 64K per SMX, and I think the read-only cache is 48K or something like that. So it's not huge, but when you're looking at individual threads and what they need for local computation, you can usually work with that. And just to really drive home the point, this is the general processing flow for when you're doing a compute application. You start everything out on the CPU, you send it across the bus, store it in your DRAM. Once you have everything set up in the DRAM over on the GPU, then you can send a command from the CPU over to the GPU saying, hey, start work. The GPU chugs on that and tries to do as much on the GPU as it can, and then eventually at the end, you send the results back to the CPU. The CPU figures out, all right, now what am I going to do with these? Am I going to kick off some more work on the GPU? Am I going to display something? Am I going to do, so forth like that, and the loop just goes on from there. And so that bus is a massive bottleneck that you really want to always keep in mind. These are some old slides that I just wanted to toss in. I already pretty much touched on all of this. One thing that I wanted to toss out, and I was actually going to spend quite a bit more time on the talk in this, but I realized that most of this, thankfully for you guys, is behind the scenes. It's stuff that's kind of a religion at NVIDIA now. Everything we do touches on power. When you guys are designing compute stuff, you won't have to think about it as much, but for us, it used to be performance was the big metric. And then a few years ago, it used to be performance per millimeter. Now what really matters is performance per watt. And we're working really hard to get that down, yeah.
Since you bring up power, could you mention why the L1 cache, L2 cache are not huge, since they do?
Yeah, so, well, power is part of it. It's also because it just takes up die space, and you don't want to use up too much die space with that. Memory is clocked differently from, so actually, that's one important point, is it used to be that there was a one clock on the chip, and everything on the chip ran at a particular clock. But that's not the case anymore. It's not efficient to do that. And so all kinds of units run at all kinds of different clock rates. And your processing cores are going to run at one clock rate, your memory is going to run at another clock rate, and you might change those clock rates dynamically over time for different reasons, power reasons, utilization reasons. And so yeah, your caches are going to be running at a different clock speed than your computation. Yeah.
What is a typical like performance per power density in terms of like gigaflops per watt or something? Like, what are you guys getting in modern GPUs?
That's a good question. I don't know the numbers. If you want to come talk to me afterwards, we can dig it up. I know mostly what I see is relative numbers. You know, it's like, well, if we take this approach, we'll shift up by this, this like it'll be 2 times more power or half as much power. If we do this approach, it'll have this effect. And so, yeah, unfortunately, I can't tell you. I do know that what we target is the way things are designed is we have a budget for wattage. We want to stick to a certain wattage, and everyone in architecture knows you don't have more than this. And different parts have a budget then. Like, all right, you guys on the compute cores, you can't take more than this. Display, you can't take more than this. Memory, you guys can't take more than this. And so then, what you're doing is you know that for your part, you've got this many watts, but you've got to double your performance over the last generation. So how are you going to double your performance from the last generation while taking half the power? And so that's part of the thing. And I'll talk a little bit in Kepler about some of the things we've done for that. But probably the biggest thing is making architectural choices, knowing that sometimes it's better to scale up an area if it saves you on overall power. And there's an example of that where we basically had these shader cores in Fermi that ran twice as fast as everything else. But because of that, the power from those shader cores was using up more than twice as much power. And we got rid of those shader cores, went back to normal cores, and just have more of them. And we have lower power and better perf as a result.
Okay, here's a question. But so for the clock throttling and the power gating, like, is there actually something on the hardware that schedule that and regulate that? Or is it just like binary, like updated values?
So
things in the power.
So there's 2 things. There's one is there's an absolute cap, and it changes for chip and for card and stuff like that. But a number I saw tossed around recently somewhere was 170 watts. We want this GPU to run at 170 watts. And what we do is we design the clocks so that we have certain benchmark apps that we know that these things are going to absolutely tax the GPU. So we run at 170 watts with these things absolutely taxing the GPU and figure out what clocks we need to set to hit that. Now you might have other applications that are still fully filling the GPU, but they're not pulling down 170 watts. So we figured, all right, we can actually clock up at that point to hit our 170 watt mark. There's also things that we do, and Apple's really aggressive about this. This is a huge part of working with Apple, is that if things aren't active, we start shutting things off. And you'll see a lot of acronyms that end in CG, like ELPG, BLPG, stuff like that. It's engine level power gating, block level power gating, stuff like that. And basically what we do is we'll turn out whole blocks of the chip off because we're not using them right now. And in mobile, this becomes even bigger. They're trying to figure out how to turn as much of the silicon off, like cut the power off to it as they can, so that if you're not using something right now, it's off. If you're using it, they see how much they can scale back the clocks until you're fully utilizing it. And once you get to the point of fully utilizing it, then they won't scale back the clocks anymore. But it should be transparent for an end user. For you guys writing stuff, you're never going to be throttled back so that you guys can't do what you need to do. We'll essentially throw everything at it until we've got everything we have thrown at it. All right, so let's see how we're doing on time. I've sucked up quite a bit. I have some stuff written down on OpenACC, and if people really want to talk about it, we can go over it. But I'm going to kind of trust that in Chris's class, or Professor Lupo's class, they've talked about this, and I'm not going to spend a lot of time on it because it's kind of stuff that you can go out and Google and get off NVIDIA's site. Also, just kind of general tossing CUDA out there or OpenACC. There's a lot of different languages now. When I was looking back when I did this talk for Fermi, and it was a much smaller list. It was basically C, Fortran, and C++ was on the horizon, and now that's changed. There's a lot more things that use it. There's also a lot more just drop-in libraries that you can go out and get today that have it built in so that you don't have to know about it. Although, since you're here, you're probably not as interested in drop-in libraries. And this is just an example of, how you would use OpenACC, how you would use CUDA to perform the exact same thing. I'm going to blow past this, assuming that everybody pretty much knows this. Oh, and by the way, this is my little dig against OpenCL. I won't say that OpenCL is awful. It solves a different problem than CUDA. CUDA is basically, going into something, what you're trying to solve, and you're trying to deal with it at programming time. OpenCL, you can actually do things that you couldn't necessarily do easily with CUDA. You can have something that's building solutions on the fly, kind of dynamic programming, and you can do that with OpenCL in a way that you couldn't really with CUDA, but the overhead to do the exact same thing is a little bit higher. So, it's just a matter of picking the right tool for the right job. If you're interested in it, I'll talk to you more about it later. But yeah. All right. Now to Kepler stuff. To me, the very coolest thing that we did in Kepler, from a feature point of view, is dynamic parallelism. So in the old days, it used to be everything you did on the GPU was told to you by the CPU. The CPU would say, all right, go launch this work and tell me when you're done. And when it's done, you collect it back, and the CPU makes the choices about what to do with those results and where to go next. With Kepler and dynamic parallelism, now you can essentially have the GPU making some calls about what it does next and where it goes. So you can keep things resident on the GPU for longer. Kind of this is the example. It used to be, right, that you would come through and you would do A, B, and C and return back to the CPU, and that was it. And now what you can do is come down and do A and B is actually going to launch off new work. And you can spawn an indeterminate amount of work. You can keep spawning stuff. You can actually have infinite work on the GPU. It's not clear to me that there's actually necessarily, with the way we can do things now, infinite interesting work to do on the GPU. But the GPU could, in theory, keep itself busy all the time with this sort of thing. And yeah.
Could this potentially be a security threat?
Are you thinking denial of service, or what are you thinking? Yeah, so it could be a denial of service sort of thing, but the software stack that controls everything knows to look out for that sort of thing. So basically what it does is it looks to see if things have terminated in a certain amount of time. And it's a configurable thing, but you can basically say, all right, this is the longest window I'm willing to terminate, or to tolerate. And then outside of that, anything related to that initial launch will get killed, and all the children get killed off. So you can, for a window, probably take over. But what's going to happen, worst case, is that this thing is going to spawn a whole bunch of new work that's going to go off the work queue and get mixed in with all the other work that's outstanding. And so you might be able to starve off other things of resources for a short while, but that's about as much of a security risk as it is. Denial of service. You're not going to have somebody else reading confidential data or anything like that, but you could have denial of service for a short period of time.
I was thinking more like spinning thumbs for indefinite amounts of time to try to delay your project or rendering.
Yeah, so that's actually something Apple's concerned about. One of the things that Apple always asks us about, and we always say that's really hard, and we can give you this, but not quite this, is preemption. They want they want instruction level preemption in compute. So they basically want to say, all right, you've just executed this one command, and before you execute the next command, we want to actually just completely page off all of your context and put somebody else in. So if you're taking too long, who cares? We'll just toss somebody else in there. So that's something that's a little bit easier to do with compute. With graphics, that's a bigger concern, because in graphics you've got these big batches of work, and the state isn't something that can easily be saved off with graphics. If you're in the middle of rasterizing a triangle, or within the shader for one pixel within that triangle, if you were to take all of that state and try and save it off, you would be looking at something like, I think I heard somebody tell me once that it would be like 50 megabytes per context to save it off. And when you only have 512 megabytes in your RAM, that's maybe not something you want to do. And then you've got to think about the time of dumping all of that 50 megabytes of state out tossing somebody else's state all back in and resuming. And so I'm not telling you that preemption is not going to happen. In fact, I think eventually it will happen. But it's always a problem that compute can starve graphics, graphics can starve compute, and there's a tension in there. And yeah, there's a lot of really smart people trying to deal with that and solve that. And a lot of my life now is taken up planning working on the next generation of chips that we're doing after Kepler, and preemption comes up a lot. So this is, to me, the most interesting slide I have about dynamic parallelism. But you had a question?
Yeah, were you saying that, is this another way of saying that it would be possible to do a recursive problem?
Oh yes, absolutely. You can do recursion using dynamic parallelism on the GPU. There's a limit to how much recursion you can do. And I don't remember, I read some documents detailing exactly what it is, but basically you can go 63 levels deep with recursion. There's an overhead though, that for every level of recursion you do, you're looking at some number of megabytes of used data for storing state or for doing something. And I can't tell you exactly what the limitations are, but you don't want to recurse any deeper than you need to, but you can now recurse.
So you don't have to have volume?
What's that?
You don't have to have volume?
Not today that I know of.
Very cool, thanks.
Okay, so this is LU decomposition, which is basically linear algebra decomposing a matrix into a lower and upper matrix. You guys have all probably suffered under this. So obviously this is something that computers are good at if it can be decomposed. So here's kind of your traditional algorithm to decompose it. And if you're going to parallelize it, you can see that there's a lot of back and forth between the GPU and the CPU. The CPU basically coordinating all of this. And it's not something in the past that you could have easily done all on the GPU. Now, today, you can basically stick the entire thing on the GPU and get rid of all these round-the-trip bus things, not just for control, but transfer the data back and forth the whole time. So that's basically good news in terms of using your memory better. Because you have this dynamic parallelism, you can use your memory better than you could have ever before. And this is just kind of how it looks from the scheduling side of the GPU. This makes it look fairly simplistic, but you can actually have pretty complex relationships between the blocks that you scheduled for work. And basically say, all right, I'm going to fire off these blocks, these blocks, and these blocks. All right, now go do this stuff. All right, wait for blocks A and C to finish, and go do these. Now we've got to wait for B and D to finish. And you can have fairly complex word graphs that are all handled on the GPU now.
Are you gonna implement this backwardsly? Can the Fermi actually have dynamic?
No, this is actually GK110 and beyond, so 110 and beyond. So GK104, if you have one of the new GK104 Kepler cards, it can't do this. This is basically a GK110 and beyond only thing. I don't know what choices they'll make about which specific chips it will be in, if this will stay in Tesla only, or if it will wind up in GeForce cards. Generally, the stance NVIDIA has taken over time has been that it's better to have compute access to everybody, because more people will develop on it, and more people will work with it. So I expect that this will be in GeForce stuff. The question is when. The first products that are going to come out are all going to be Tesla, and they're all going to go to Cray. But then after that, and it comes down to die stuff. I mean, the sad reality is Cray's going to, well, I don't know about Cray, but people will pay $6,000, $7,000, $8,000 for a really high-end card that has a perfect chip in it. The GeForce we can sell for $1,000. You don't want to take all your perfect chips and put them in a GeForce then. And so it's going to be a little while until all of this stuff really trickles out. That being said, it might be a matter of a couple months, it might be a matter of 6 months. I don't know that in the business, so I can only guess. So this is another example. In the old days, you would have had to have gone and computed pretty much overkill for every pixel. Now, with dynamic parallelism, you can basically have the GPU make choices based on the data about what it wants to do. There's a demo that was shown at GTC last week called the Galaxies demo. I've got the video on here if people want to stay afterwards and see it, if we've got the room for long enough. And I'll actually fast forward to just a picture of it really quick. I should have had it earlier in the slide sequence. So it's, with Fermi, we showed this demo called the in-body demo, which basically had some, at the time, large number of particles. I think it was like 2,000 particles or something like that. And we're all swirling together. And it was an n-squared problem, where every particle was interacting with every other particle, gravitationally speaking. And it was something really cool at the time, that there was no way you were going to do that with the CPU, and previous generation GPUs just couldn't have done it. So with Kepler, kind of to raise the bar and show off, this is another in-body demo, but instead of 2,000, it was 280,000. So for n-squared, you can see that that's kind of painful. And there is a lot of computation going on, but because of dynamic parallelism, you can also prune out a lot of things that aren't interesting. And this is kind of a behind-the-scenes wireframe of some of the acceleration grids. And I don't know this algorithm, and I can't explain it to you in detail, so I'm doing a little bit of hand-waving here. But if you know some idea of how in-body works and these sorts of things, you can guess about how you might prune things out. And so you also can kind of guess why I think this is kind of the coolest feature we've got in Kepler. There's a lot of other features, but I kind of think that that's the killer app. And this is just kind of talking more about the same thing. Since we're running a little low on time, I'm going to blow forward a little bit. You were asking, somebody back there was asking earlier about feeding work, and this is basically how it does. There was Fermi that we talked about earlier. With Kepler, we can basically take things directly from here, feed it back into the grid management unit, which keeps a really large list of pending work that it can choose from. And part of what its work is figuring out, all right, what are you waiting on? Are you waiting on other blocks of work to complete? Are you waiting on memory to complete? Are you waiting on, basically, what are you waiting on? Are you available to go? And taking whoever's most available to go and sending them into the work distributor to send out to the various SMs. And so there's a lot of logic, although a surprisingly large amount of the logic about how to schedule and when to manage can now be done in the compiler. And some of the power savings that we have in Kepler is by offloading some of the logic that we had in Fermi and hardware into the compiler, where the compiler actually knows ahead of time exactly how long certain things are going to take, and we can schedule based on that. I'm going to kind of blow by that. The last thing I'll touch on really quick is just HyperQ. And HyperQ is one of those kind of irritating marketing names, but the basic idea is that if you've got a lot of different tasks running, now instead of doing one task at a time, even if you could have done multiple kernels at a time within the same task, now you can basically fit as much onto the GPU at once running concurrently as you possibly can. Which means you can have apps that are operating together where you couldn't have before. It also makes virtualization interesting. And I know this is one thing Professor Lupo was talking about is if you have a data center that has virtual machines running on it, you could have one GPU and a whole bunch of virtual machines all running on that GPU. And so instead of all of you guys waiting for the machine that's got the good card, you guys can all be running virtual machines on the machine that has the good card doing your development at the same time. So in theory, that can be a pretty big savings. All right, so these are kind of generic wrap-ups, but one thing that is interesting, and I don't know a lot about this, but just knowing that it's there is kind of cool. Apparently Stanford has what sounds like a virtual GPU cluster that you can go and use. So I would encourage people to look into that. I don't know any more details than what's on that slide. I found that slide, I was like, oh, that's kind of cool. And that's that. In CUDA 5, there's a preview available. All of this, well, you can't use any of the dynamic parallelism or any that without GK110. But there's still a lot of cool things in CUDA 5 that don't rely on just having GK110. There's a lot of tools, especially, that are out there that make things nice. And so I encourage people, if you're interested in this, to go download it, become part of the development program, and give feedback, what you like, what you don't like, what you find really frustrating to learn with, and so on. All right, now that I've run through a lot of time, hopefully there's enough time for some questions if people have them. I've got more slides to go on afterwards if people don't have questions.
So let me, before the questions start, I know that some people have to run to class. Those of you that do, thank you for coming. Let's thank the speaker and then we'll do questions afterwards.
So, do you think that the bottleneck that you have with the PCI bus is sufficient to drive the adoption of like system on a chip type architectures?
Sorry, what's that?
Like, do you think the bottleneck that you have with the PCI bus between your processor and your CPU is sufficient to drive the adoption of like system on a chip